Thank you for the opportunity to come and speak today. This is actually my first speaking engagement since I retired on the 1st of April. So officially no longer Colonel Trent for the first time. And so it's a little awkward. But I'm going to share some insights with you here. I think this is, hopefully, is this sharing correctly, Dan? See a title slide?
Looks
okay.
Looks right to me.
So what I'd like to talk with you about today is the concept of human system integration being instrumental for trustworthy artificial intelligence. And in taking a look at some of the talks that you've received already and some of the material that's going to be shared in this panel by others and then further expanded upon tomorrow, there's a common theme here of failing to design for humans can result in unfortunate outcomes, and design doesn't just anymore end with a system in operation. It also must include considerations for how that system will be monitored in performance. So I'm going to start with a couple lessons from industry. Many of you are familiar with a couple of these. I'm going to talk about the Tesla and the Boeing 737 MAX as just recent contemporary examples of complex automation failing in the hands of users that didn't have a full appreciation for what it could or could not do. The Tesla autopilot system, it's intentionally in sort of smear quotes here, isn't in fact an autopilot system, although it's marketed as such. And as a result of consistent and early failures of this system, countries such as Germany have acknowledged that it's a misleading label placed on a device that can lead to, again, unintended outcomes, because users fail to understand how it's strong or weak. What I have on this slide is a depiction of the A panel, the dashboard immediately in front of the driver, that shows sort of normal operating feedback for a vehicle, but then it has this nice dramatic picture of a person, holding the wheel. This is a warning that pops up when it senses that you're not holding on to the steering wheel while the car is in this sort of autopilot or driver assisted automation assisted driving mode. So this indicates the notion that you're actually not supported with an autopilot system in which you can go and tend to other things, but you're actually have been relegated from an active controller task to a vigilance task of just monitoring a system that gives you very poor feedback and expected to take over when that system can no longer compensate. Tesla will offer we're just a few tests away. We just need a couple more cycles on our computer vision algorithms. Our operators just need to be smarter. We're operating at a lower failure rate than other vehicles, but in fact, the actually meaner the deaths in crash rates of the Ford Pinto in the 70s. The takeaway here that leads into my second example is that we must be very clear about what systems are capable of doing and are not capable of doing. That when we provide misleading labels, the people that are most impacted by those labels will suffer the most. The second example that's in this vein is the 737 MAX. Boeing, in competition with other leading commercial airline companies, saw a need to deliver a modern replacement for the venerable 737 airframe, which is traditionally very reliable. Their goals, as many of us acknowledged, were unachievable. Find a good solution fast and make it cheap. Their notion was of good was a new airframe that would require no new training on the part of the pilots. They were in direct competition with Airbus. Airbus and Boeing were on target to deliver their aircraft about the same time, and so they wanted to make sure that any design changes didn't slow their pace to market. And they would make this aircraft cheaper for consumers by reducing fuel consumption. The fuel consumption goal would be achieved by installing a new turbine engine. You can see the picture here in the middle of the slide shows the legacy turbine, which has a slimmer profile and it has lower power, but it also uses more fuel than the new turbine engine, which is depicted on the right-hand side of this illustration. Well, the challenge when you install a turbine engine on a wing of an existing platform is that if you change the profile of the engine, you change the flight characteristics of the airplane. Normally, this comes with a training cost to the pilots, but if you're going to try to avoid the conception that this is a new aircraft, you're going to want to engineer out the changes that the pilot will recognize. And their solution to this problem was of changed aerodynamics was to introduce a piece of automation, the maneuvering characteristics augmentation system. Sounds like a military system, where we just cram a bunch of big words together to form an acronym, MCAS, that will sound so innocuous that people won't worry that it's there. This solution was a piece of automation, some software on an already complex aircraft that would monitor angle of attack sensors because and these are sensors that help you the pilot, the aircrew determine is the plane climbing or declining. These angle of attack sensors will help indicate whenever the airplane thinks it's going to stall in the case of a significant incline. And it will automate the trim corrections, in other words, adjusting the wing without involving the pilot, because we didn't need to train. We're not going to train the pilots on anything new here. This is just a piece of software that's going to make things simpler for the pilots. It's going to keep things operating in the same way it has in the past. Well, what happens whenever those sensors, the angle of attack sensors, fail and you have bad data going to the software? The software makes bad decisions on how to compensate for conditions that may or may not actually exist, and you end up with these two aircraft, Lion Air Flight 610 and Ethiopian Air Flight 302, crashing after a series of violent inclinations and declinations. This was all under the premise of, again, delivering what will make life better for the operators and the passengers involved, while not changing and in fact masking the complexities of the system. And so when we talk about human-system interaction, human-system integration, and artificial intelligence, we have to realize that what we're actually doing is creating increasingly complex systems that become increasingly difficult for the everyday person to understand how what is it going to do, what has it been doing, what's it going to do next. And so the introduction of terminology that by computer scientists in the last 10 to 20 years has actually obfuscated the notion of what the computer is in fact doing. In both of these cases, whether it's a passenger driving a Tesla or it was the air crews with the 737 MAX, the users in this case had a very difficult time understanding what the system was doing. The pilots, for instance, had a really difficult time understanding why was the aircraft nosediving or why were stall warnings going off when the aircraft was in fact flying levelly. They could see it, they could sense it with their physical senses. Of course, the Tesla drivers were wondering, why is this autopilot system speeding up whenever I'm approaching a dangerous vehicle or not navigating around structures that I can clearly see are dangerous. So these labels that have been introduced, like learning, perceiving, predicting, paying attention, have a way of misleading, on the everyday users. They're words that have real meaning to us in everyday life. When I send my third grader to school every day, I don't think that she's actually tuning coefficients that will only apply to a mathematical algorithm that's performed for a certain finite use case. I view learning in a human as a generalizable construct in which mental models are able to be built, destroyed, reframed, acquired in a way that applies to new use cases. And in fact, that's not anything that's happening in artificial intelligence systems. I don't think of perceiving as classifying data. I don't think of predicting as calculating probabilities. I've had great discussions with mathematicians that talk about predictions as calculating the probability of a state in a data source. Well, most people think of predicting as some assessment of a future state that is yet to happen. Calculating a probability that something exists in a data set is, most people would think of as predicting the past. So these labels, I believe, in what we're seeing in reality, cause people to misperceive and misunderstand how they should trust and how they should interact with these systems. They play into this notion of the substitution myth, which human factors engineers over the last 30 years have demonstrated is a fallacy, that technology never in fact replaces humans, that good resilient systems and designers of these systems recognize that humans are the source of resilience, that they're not something bad to be engineered around. They're not full of evil intent and unproductive biases. They're actually highly efficient at processing information when it's presented to them in a context appropriate way. But these are design features that our artificial intelligence evangelists are often overlooking, mostly because they haven't had a lot of experience with complex systems engineering. We recently, over the last few years, one of the first things we did at when we were standing up the Joint AI Center is we recognized that there was a tactical risk that the JAIC might not deliver enough good technologies to be perceived as useful. But the strategic risk was that we deliver lots of things that appear to be useful, but they fail in situations of high consequence. And I'm sure Jane, who follows me, will talk more about this crusade that we've been on to institute a campaign of testing and evaluation. One of the other elements that we recognize is we should be able to talk to the public about the ways AI should be implemented. And so we came up with a publishable document after much open discussion that resulted in 5 AI principles. I put them on this slide, and I've spoken about this in a number of different venues, really just to illustrate that what we had published with the DoD AI principles was nothing different or unique than engineers have recognized for decades about resilient system characteristics. If you design a system that is opaque, that is not directable, that nobody can understand, that's not really useful for the real world work and the real people that have to use it, it will fail. Or it will be misused in unintended ways. And so what I like about this, this period of time is it allows us to leverage AI as a new feature of technology to reintroduce the qualities of good systems engineering. So how do we do this? This is where I'll wrap up and pass it on to some of my colleagues here. The first sort of gospel that I'll share here is the gospel of human-centered design. In the Joint AI Center and in Applied Research Lab at US Cyber Command, that I stood up previous to that, and now in both a commercial and an academic role, I've led efforts to institute what I call mission engineering. This can be found in commercial software development as sales engineering, but it doesn't really go over that well in a military setting. So mission engineering is a deliberate interdisciplinary effort to understand and articulate requirements in a way that the Defense Department just doesn't do today. We write Word documents that can be interpreted in a variety of different ways by contracting officers, requirements managers, and then the developers that have to make the system. And so human-centered design has been effected through campaigns of mission engineering that result in digital prototypes. And this is one of the efforts that I'm happy to actually be helping the Office of Secretary of Defense for Acquisition and Sustainment to introduce as a department-wide concept for how we can arrive at technology solutions that are human-centered in efficient, effective ways. This relies on two types of engineers that to be included upfront in the design process that are normally left to sort of late stage development testing or maybe in fact forensics on why the system failed in the real world. Human factors engineers and test engineers need to be brought in to the design process. We can't wait to determine how the system will be tested in operation, because it will be too late to introduce instrumentation. That gets to my second point about AI assurance testing is in fact human machine performance testing. If our legacy systems in the military have been designed without the capability to document, to sense characteristics of this human machine system that are important for determining how it will succeed or how it's about to fail. And as we introduce these increasingly complex AI-enabled systems, that can't happen anymore. We have to be thinking about how we're going to engineer in continuous monitoring rather than thinking of test engineering as a discrete activity that happens in a life cycle only to deliver a test report that allows it to move forward. And then the final sort of gospel here that I'll offer is that like we were in the 80s and 90s with the introduction of the internet into the workforce, we right now for artificial intelligence are very busy at delivering the internet. We're not anticipating all of the roles, all of the support roles that will be critical for ensuring the internet or artificial intelligence in our decade will need to succeed. There's inherently technology introduces new roles, new support requirements, new needs for skills and knowledge. And we're not necessarily designing technologies to enable these emergent roles. Roles like the model maintainer. Somewhere in the fleet of Teslas, there will be the need, or a fleet of autonomous vehicles that are fully autonomous, there'll be the need for somebody to easily monitor the efficacy, the fitness of the AI models in production. And how can that person interact with the system, whether it's one autonomous vehicle or it's a fleet of swarming UAVs? Similarly, we recognize in the Defense Department the need for better data engineering in order to enable our production data to be used for the design, development, or testing of new systems, but also to ensure that we're actually collecting the kind of data that our system will rely on. So how are we enabling that support role? That non-user, but is in some ways he or she is a user. So what I'm articulating here is the supervisor of autonomous vehicles, the data engineer, the model maintainer, they all represent roles that don't exist today. And this requires an equal amount of research attention as our focus has been on new AI algorithms and how to modernize compute and storage capabilities. So I'll turn the mic over to our next speaker for their portion here, or I'm happy to answer any questions about this either now or later.
Great, thank you, Stony. That was a great talk. I'm not seeing any questions in the chat. People can feel free to ask them, but I do have one. So I thought your point about kind of the the demystification of language around AI has kind of anthropomorphized or led to unreasonable expectations about these capabilities. I was wondering, do you think the solution is finding different user-friendly language, or do we just need to get our decision makers smarter on kind of the jargon and terminology of what these systems are doing? Over.
I think it's, the English language is certainly malleable, but, our technologists have to use language appropriately. We talk about this, in the military a lot. Words matter. Doctrinal terms are useful because they establish common knowledge, and ease, communication, especially when in conditions of high consequence. And so, my recommendation on this is that we understand that, people generally think of, vision, of learning, of perception in established ways. And so if we're in fact not talking about learning, vision, perception, attention, then we need to think of, more accurate labels for those. Because it's not just our decision makers that are impacted by this. It's the novice, uninitiated user that will need to be able to pick up a device, and utilize that to maximal effect. And so if he or she already starts from the notion that I'm operating an autopilot system, and it's not in fact an autopilot system, then we're already starting from at a deficit, at a common knowledge deficit.
Great, thank you. And I believe Jane's going to be talking a little bit more about novices' mental models in a little bit. So I think that's a great tee up. So I'm going to move on to our next speaker, but thank you, Dr. Trent. So our next speaker is Dr. Joseph Lyons. So he is joining us today from the 711th Human Performance Wing out of Wright-Patt, where he serves as the lead for collaborative interfaces and teaming core research area. Dr. Lyons has his PhD in industrial organizational psychology from Wright State University. And he has a particular interest in human machine and interpersonal trust, human factors, and influence. Since 2005, Dr. Lyons has provided his expertise on these topics to AFRL, including serving as the program officer for AFASOR, an associate editor for the journal Military Psychology, and making numerous contributions to the academic literature. Please welcome me in welcoming Dr. Lyons.
Great, well, thanks for that intro. Just a quick check, can you see my slides okay?
I can see your slides okay. You chopped out a little bit on your mic, but I think just proceed.
Gotcha, thank you very much. So it's great to follow the talk Dr. Trent provided earlier. There's a lot of nice little parallels with the things that I'd like to say here today. So in motivating this talk today, within my position within the Air Force Research Lab, I'm often asked, when would you give an important decision to a piece of autonomy or a piece of AI, or even just a piece of automation? And so I decided to make a talk out of it, just to help with the conversation a bit. And so the bottom line up front is this chart right here, which is full of interesting, potentially scary things here. So this is kind of the answer to this question of when would I allow a software or an AI in this case to make an important decision? And I thought about this and I put this list on paper, and I wouldn't expect any particular program or any individual or organization really to do all of these things, but these are the things that come to my mind in terms of when I would allow a piece of intelligent software to make a decision that's important, a decision that has some stakes to it, where there are some consequences to the decision. So what I'm going to do is kind of walk through each of these a little bit to try to start some conversation and hopefully answer some questions when folks are ready. And so the first issue is really having sufficient transparency. Dr. Trent mentioned this a little bit in terms of understanding what's going on with the system, but so what do we mean by transparency? Transparency is really a set of methods for establishing shared awareness and shared intent between humans and machines. This could be applied to automation, robots, AI systems, anything that has some level of discretion in terms of how it interacts with you. And so let's break this down a little bit. What do we mean here? So naturally, performance thresholds. What is it good at? What's it bad at? In the literature, the issues of reliability and performance, these remain the key attributes of what drives trust perceptions or distrust perceptions, if they're negative, of course. So we need to understand across a range of tasks, what's it good at, what's it bad at, okay? Also thinking about things like intent. What do we mean by intent? So what expectations should I have of this technology, right? So what things should I anticipate this technology is going to do? How should I anticipate this technology is going to interact with me? Because we've shown through published research that the ways that systems interact with us, both from an etiquette standpoint as well as a conferred benevolence standpoint, they actually matter. You know, even though these are just machines, the way they interact with us and the communications that they give to us make a difference in terms of our cognitive workload, in terms of our perceived trust and trustworthiness of these systems. So these sorts of things matter. You know, what expectations should I have? What's the overall intent of the designer? So this kind of goes to the business case for why do we need this technology at all? You know, this is probably one of the last things that most engineers might think about, but the users, the folks that are actually using the system, want to know, why do I need the system after all? I mean, a lot of military folks, they are often handed tools. It's like, well, why do I need this? What difference is it going to make? So this gets to the issue of the business case has to be important for generating acceptance of the technology, right? And also the intent issue goes both ways, right? What expectations does the technology have to me? So if I'm driving my Tesla, you know, what does the Tesla expect of me as a driver? Does it expect that I can react in a threshold of 10 seconds or 5 seconds or 3 seconds? Does it expect that I'm going to be able to recover in really harsh and uncertain circumstances? So understanding and framing these in advance is a really important thing that we should be doing with our technologies, right? Again, what are the expectations from me as an operator? Also thinking about things like training, the pedigree of the training. This conference with DataWorks, there's been a lot of discussions about testing and how to do this appropriately. I would really like to see training, in particular the pedigree of training, become another form of transparency that we can use in making inferences about a technology in terms of whether we should be using them or not using them. These sorts of things are really important. You know, what kind of testing has been done? How much testing? These are things that we could create as sort of metadata for understanding the transparency of the system. And of course, also decision logic. You know, what are the assumptions that the system has? Why is it acting in the way that it does? I'll talk about some other nuances with that in a second, but you know, understanding decision logic is important, but the key consideration here is that the things that you might need as a designer are probably different from the things you might need as a tester, which are probably different from the things you might need as an operator, right? So we need to think about these different kinds of information and how we might try to give that decision rationale or the decision logic across the range of potential operators or testers or designers. The next issue involves a sufficient experience. And how do we know when we have sufficient experience, right? So we need to be able to test across a wide variety of contexts, and understanding the edge cases, essentially, the constraints, those are really what we should be using to drive the sort of context that we use within our tests, right? So we really think that machines should be stressed in as many possible situations as feasible. We understand that you're not going to be able to test every single situation that's not tenable. We understand that, but that makes this activity of trying to understand the edge cases all that more important. We need to really put thought into what's the spectrum of constraints that we need to consider here. And one little anecdote I like to give here is I've done a lot of work with fighter pilots in terms of understanding trust of not only other fighter pilots, but also trust of technology. One of the key things that I've learned is that trust is not driven by temporal issues alone. So if you ask a pilot, hey, you get a new person into their squadron, how long does it take you to build trust with this person? And the answer is always like, well, it depends, right? What does it depend on? It depends on whether that person has been put in a situation of high complexity and I've observed that person handle it effectively, right? So it's more event-based, it's not so much temporally based. This is something I think we should really think about in terms of understanding what are those key events that we should focus on within our tests, right? Because these things matter considerably. With machine learning, so Dr. Trent mentioned the issue of labeling something as a machine learning system. This is a pretty important issue because of course the training issues that comes into play. So how much training data is sufficient? And also, can we start labeling our training data almost as a form of transparency to say, what's the kind of variety that this training set has in it? Are there things that are missing? Are there things that might promote bias? How recent is the training data? You know, what assumptions does the training data have that we might want to consider as a community? These are all things that we could consider as almost a form of transparency for the training itself, right? thinking about the track record of high performance. So again, the issue of demonstrated reliability and performance is a strong boost for trust, right? If you've got something that's highly reliable and you've seen it perform well, you're probably going to trust it more. But one of the things we need to consider here is that that experience doesn't need to be directly experienced, right? It can be indirectly experienced through social groups. And this was something that we observed within the fighter pilot community, that a really positive event or a really negative event can carry over to other groups that didn't actually experience that, but they've heard about it. They learned about it through stories, through narratives, through perhaps shared data, things like videos that really pervade this issue of trust or distrust. It can go both ways for sure, but it's very much a socially driven process. And so what this means is that we should really try to follow systems after they're fielded. That's in some cases where a lot of the hard work starts, because we've got to understand, okay, what are they actually doing in the real world, right? How are operators using them that weren't anticipated? Because we've got to understand operators are very clever, they're very creative, and they're very time constrained. They're going to use things in ways that we can't anticipate every situation in the test process. So we need to follow them after test to try to get some of this data in terms of what's going on. We also need to understand that objective performance, the actual objective performance of a technology, is not the same as the subjective perceptions about the technology. You can have a technology that's performing great and still experience some distrust and suspicion from operators. You need to really understand what's the core of that. Why? Why are they suspicious? Why are they distrusting of the technology? And get to the bottom of it. You can only do that by going out and collecting the data, right? Talking to people and getting that kind of data. Also thinking about the attributions of technologies that fail. In most cases, I would say, we're going to have technologies that make errors. It's just the reality. We're not going to have perfect technology. So what do we do when systems make a mistake? We need to be able to understand why it made the mistake and attribute the errors to that particular cause. And of course, it's got to be done with integrity, so that's actually an honest assessment of what happened. But this is a really important thing, because if we can attribute the cause of the errors, we probably won't see as great a decline in trust as we might otherwise if we don't understand why it made that mistake, right? And of course, poor design, things like this, they can lead to lack of transparency, which can make it hard for an operator to understand why the system screwed up. So this kind of goes back to the issues of transparency. And I need to definitely speed up here. Understanding errors, and in particular, the stability of errors. So errors, this is something that a lot of people come to me to talk about. When should I show the operators, hey, this system is imperfect? Well, always, showing errors is not necessarily a bad thing, especially if they're stable, if you have predictability, right? So the stability of error doesn't mean lack of error. We just need to have predictability of error so we can understand when to use a system and when not to use it, right? So in understanding this adds that predictability. So one of the things, reflecting back on Dr. Cummings' keynote talk yesterday, it was scary how the amount of variance that the cars had in terms of their errors. They were erroring all over the place, and the lack of transparency for why they were making mistakes. That's really kind of scary, and we need to try to do our best to overcome those issues. Also understanding that error types are not all the same. You've got misses, you've got false alarms, you've got easy errors versus hard errors. You've got errors that occur early versus later. So even one of our panelists on this panel, Purniva Madhavan, has done some work on the issues of errors and how they implicate trust and distrust, right? So the kinds of errors matter, and we need to take that into consideration as we're fielding new tech and collecting this data, right? I'm gonna move on to the next. Thinking about machines as a partner. This is an area where there's a lot of research going on right now with human autonomy teaming, human machine teaming. This is where I think there's also a great need for research, because there's a lot that we don't know, right, in the space of human autonomy teaming. But understanding some of these things has huge implications for how humans interact with and the expectations we have of machines. So, for example, understanding how the agent understands its role. For it to be a teammate, it's really got to take on a role within a team and be able to communicate on behalf of that role towards some common goal. This is one of the really good definitions put forth by McNeese and colleagues. And understanding that role has a lot to do with communication and expectations, right? So that's a huge issue with understanding human autonomy teaming. Understanding dynamics. So understanding, for example, agents that are followers versus leaders. How can we avoid this massive overtrust that we see indicative of human-robot interactions, right? So great research by Robinette and colleagues that showed that people oftentimes are way over-reliant with robotic systems. How can we avoid that? How can we instill that into our designs to try to overcome some of this? Issues of learning systems, as I talked about before. Labeling something as a learning system has implications in and of itself. We've actually got data that shows if you tell people that some strange behavior that a system, that they've observed a system occurring, is actually the result of a machine learning algorithm, they might trust it more just because they think it's a machine learning algorithm. They think, well, the machine must know what it's doing. It doesn't make sense to me, but it must know. It's a machine learning system, right? This is scary. This is dangerous. We need to be very careful about how we label our technologies for reasons such as this. We don't want to misattribute capability where it's not actually there. And of course, team processes are critical here, and understanding team roles and how they might shift dynamically. Also understanding things like social affordances. So there's a great deal of research, especially in human-robot interaction, looking at kind of social affordances, you know, expressions, facial expressions, emotional understanding, things of that nature. We need to be really careful here to not make people have expectations that aren't real. When you give people an anthropomorphic face, for example, that drives expectations. It makes a person view something as perhaps more capable than it really is. We need to be really careful about that. I'm not saying that we should never use these things, but we need to be really careful that we can make sure people's expectations are aligned with the actual capabilities of the technology. And knowing what's acceptable. This is critical because we need to understand norms. And real quickly, I'll just point out that Murphy and Woods in 2009 put out a nice paper on an extended set of robot laws. I know most of us are familiar with Asimov's laws of robotics. Well, take a look at Murphy and Woods. They've actually got some really interesting stuff to say that are more focused on humans and expectations and appropriateness. So what's key here is trying to understand, what does appropriateness mean? What are the norms? Understanding context. How can they respond appropriately in that particular context is a pretty important and critical thing, especially as it comes to machine ethics and things like of that nature. And finally, as I'm running out of time, I wanted to close with one quick example from the Air Force of an example of a technology that's, I think, a really good example of human autonomy teaming. This is the impact system. Essentially, it's a UAS command and control technology, a set of software that has an HMI, an agent architecture in the background that helps facilitate things, and of course, a software architecture that facilitates the crossover interactions between the agents and the humans within the HMI. I think this is a good example because it allows the full, what we call the full spectrum of teaming, right? In this slide, the full spectrum of control is how we depicted it here. Everything ranging from very manual operations, I want a UAV to go out and scan this area and do X, Y, or Z, to play calling where you can say, I just really need this to happen. And the intelligent agents can come back and say, here's some options for doing this. Which of these would you like to select? And oh, by the way, here's the strengths and weaknesses of each of these options, right? It puts the information in the hands of the human operator, and the human can decide. It arms them with useful information and allows very timely comparison across different courses of action. And finally, all the way to the top, we can see the fully automated play initiation. And in this case, based on a very human-centric model of the task, the automation, in this case, or the intelligent agents, can respond automatically to things that they perceive that happen, triggers essentially that happen in the environment. And in this sense, it gives it the full spectrum of teaming, the full range of control there. And of course, throughout this entire full spectrum of teaming, the humans have observability and directability of the entire process. So they can change anything at any time within that entire spectrum. And with that, I will close because I believe I'm out of time.
Yes, great. Joe, thank you very much for that. As always, I like the work you're doing. I don't see any questions in the Q&A or the chat, but I do have one. So we have a lot of, I think, working level testers in the audience. And I know they're not quite here yet, but they're definitely coming down the line. A lot of systems where this issue of trust and reliance is going to be really relevant. Do you have any advice for those people in the audience about one big thing they can consider doing differently when they're planning their tests? Over.
So one different thing that the test community might take into consideration, is that kind of what you're saying?
Yeah.
Yeah. Funny thing is, I think a lot of this starts at the use case of what are the scenarios that you want to test. Understanding the spectrum of complexity, I think, is a really important thing that they might be able to pull in. And this is in reference specifically to autonomy, because I know that's one of the big things that people are asking about a lot. How do you test autonomy? Well, understand first, what's the spectrum of contexts you might want to consider, and don't neglect that, because oftentimes it's something that the scenario development comes after. Let's do that first. Let's do that step up front and see what range of things we might want to test to begin with. I think that's a useful potential thing.
Great, thank you. And Joe, it looks like there's a question in the Q&A about one of your references. If you don't mind typing out a response to them, that would be great.
Oh, sure. I'll take a look at the Q&A.
Great, thank you. Okay, so our last speaker before the panel is Dr. Jane Pinellas. Dr. Pinellas has her PhD in statistics from the University of Michigan. Go Blue, and sorry, Stony. For the last decade, Dr. Pinellas has provided this expertise to the national defense community, including to the Marines, leading the test science group at IDA, as the head of T&E for Project Maven, and now as the chief of test evaluation and assessment for the JAIC. Jane's always been a strong advocate for human factors in the department, and she'll be telling us now about the JAIC's efforts on that front. So please welcome me and welcoming Dr. Pinellas.
Hi, everyone. Hi, Dan. Thank you very much for having me here today. So you can see my slide and you can hear me okay, correct?
Correct.
Okay, wonderful. As Dan mentioned, I'm the Chief of Test and Evaluation over at the Joint Artificial Intelligence Center. Our goal is really twofold at the JAIC. One, we objectively and rigorously test JAIC's AI-enabled system, but our second, equally as important goal is to proliferate whatever knowledge, tools, and expertise that we ultimately derive from testing our own products and hopefully spread to the rest of the department. So with that in mind, this talk today is obviously on human system integration. And specifically, I want to focus on what one should consider in a TEMP. Many thanks to my IDA colleagues for putting this talk together, Rachel, Dan, and Brian. So, and Stoney gave a great introduction to this, despite his OSU roots. Many people have the idea that by the virtue of offloading tasks from our warfighters to AI-enabled systems, we might care less about HSI. In fact, that's really not the case. In fact, what we're seeing is warfighters will still have to interact with the system in some capacity. And now that system is more complex, more difficult to understand and predict. And oftentimes the decisions that have been delegated to it are actually also more complex and more consequential. And so it becomes that much more important to utilize these few opportunities for our warfighters to understand and predict what the system is doing, to intervene and troubleshoot. And so these touch points become more important than ever. So with that said, what we'll talk about today is a rough overview of what the Hsiai framework looks like for the JAIC. We're still in the process of briefing it around the department and even to our JAIC leadership to try to kind of get buy-in and see if we can turn this into a department level view of HSI. I'll delve into a few select topics here. You see 4 topics listed: mental models, workload, trust, and function allocation. That's just a biased sample of the rest of the framework. And we'll talk about the current state of HSI in complex systems. Oops. I'm jumping right ahead here. So when it comes to supporting our warfighters, we tried to structure our HSI framework in the way that our warfighters achieve their mission goals, that is through the OODA loop. And so the idea is here that the warfighter must observe, orient, decide, and act in order to accomplish their mission. HSI in theory is about making sure that the technologies we give our warfighter at a minimum preserve their current levels of performance and hopefully actually enhance the performance. So when it comes to the first two steps of the OODA loop, observe and orient, we hope that our systems help warfighters understand and anticipate situations. So here we get at the notions of predictability, understanding, of timeliness of information, and of the ways in which the information is conveyed. When we get to the decide piece of the OODA loop, our systems must support our warfighter as they make decisions. So we must accurately describe the decision space and inform their decisions about employment of the system. And then when it comes to act, our systems must empower our warfighter to act upon and carry out their intent. And so here the system hopefully is helpful in carrying out the warfighter's intent. Now, if you look at these closely, and especially the way that my team has worded these, what you'll see is that there's an obvious tie-in here between HSI and the DoD AI ethical principles, because the idea that a warfighter truly understands their current situation and is able to make good decisions about system employment basically is very closely related to the responsible AI principles. And so if we want to have a kind of a test framework that addresses multiple issues at once so that we test quickly and efficiently, then it makes sense to tie a lot of this to the DoD AI ethical principles. And in fact, that's exactly what we see here. The three core HSI needs that we've identified map very directly to some of the components of the DoD AI's ethical principles. You see again that observe and orient, the idea that somebody understands exactly what they need to understand when they need to understand it, maps very much to the traceability of how someone makes their decision. You see also that the ability to make good decisions comes with a responsibility. And then finally, the ability that you can get the system to do what you need it to do is tied very closely to the governability responsible AI principle. And again, if we want to quickly and comprehensively test and evaluate our systems, then it's great that we can combine these as opposed to stovepiping these different concepts. So why did we need this Hsiai AI framework? And what do our products look like? What will they address? Well, we need it for a couple of reasons. One, the department does not really have anything formally written down and enforced as a way to test even software-enabled systems, let alone AI-enabled systems when it comes to human factors. Probably it's not surprising to anybody in this talk that it's an important missing piece of the testing puzzle. But at the same time, what we're finding is that the expertise that's needed to test these systems in these ways does not reside in the traditional T&E disciplines, right, of systems engineering or perhaps statistics. And so what we're seeing is the department really doesn't have enough expertise. There's absolutely not enough to go around when it comes to human system integration. And so our job then becomes to leverage whatever we can and to empower our non-experts to get to a reasonable solution. We have to figure out how to test and evaluate the HSI characteristics of these novel systems, acknowledging that most test teams will not have a resident HSI expert. And so the purpose of this framework then is to provide a practical tool to empower these non-experts to at least reach a decent solution. So in order to accomplish this goal, we are proposing 4 products. The first one will help working level testers write and evaluate whether temps, test and evaluation master plans kind of have at a high level key HSI concepts listed and evaluated. The second product will be a deeper dive into these topics intended to give non-experts a reference in terms of detailed test plans. And then the last 2 products will provide working level testers with more resources as far as practices, as far as policy, software tools, widgets, etc. For the rest of this presentation today, we'll just focus on the high level guidance. Uh-oh, there we go. my computer, of course, decided to be slow, specifically during this presentation today. So under our framework, which again, mostly we're not going to be briefing here today, this is how we've grouped some of the concepts relating to HSI under the OODA loop concept. Of course, we won't get through these today, but just to give you an idea of just how big this the scope is of our framework. Today, we'll focus on a piece, again, selected probably with some bias from each of these. So we'll focus on mental models when it comes to observe and orient. We'll focus on trust and reliance and workload when it comes to decide. And we'll focus on function allocation in the act piece. So let's start with observe and orient, and we'll start with mental models. The mental model for a warfighter is their set of knowledge about the system. So it allows them to reason about things and make predictions potentially about system behavior. And if you've heard me talk about the importance of this before, I would argue that predictability of a system is probably one of the biggest manifestation of what some people call trustworthiness for the warfighter. In other words, the warfighter needs to be reasonably confident that if you input X into the system, Y will come out under certain conditions. So as testers, really what we want to get at is the idea that a warfighter is able to predict how a system will behave in certain circumstances. And the ability of the warfighter to anticipate systems actions are critical to them determining whether it's appropriate to use the system and how to coordinate to achieve mission success. The problem is, or one of the many problems is, that there are different groups of warfighters and they will have differently formed mental models. And a single test with just one group of people will likely be insufficient to fully characterize performance. For instance, consider this AI that we have depicted on the left. In its processing world is depicted during this nodal graph. And now consider an experienced warfighter who is trained on a legacy system. So that person obviously has a predefined mental model of the system's behavior based on their prior experience that may or may not have a lot to do with the actual system at hand. On the other hand, if you take a novice operator who has recently went through training with the system at hand, we might expect that they have a general idea of the system's core functionalities, but they're unlikely to be able to predict systems behavior outside of very common tasks that they have seen a lot of. And then finally, if you think of an experienced warfighter who has work experience with this specific system, they might have a much better understanding of how the system works. So testing warfighters with different levels of experience will yield different performance results, and they can't necessarily be extrapolated to any other groups. And of course, no matter how experienced the warfighter is, as you see in this last case, it is unlikely that they will ever be able to fully predict the system's behavior. Testing must determine whether these mental model gaps exist and whether we need to address them either through design changes or training. So moving through our OODA loop to the decide piece, we move to trust because we are trying to show whether to measure rather whether the warfighter is able to trust the system to make good decisions. So trust has over 300 definitions if you try to properly define it. And so here we've identified one of them. We define trust of a system as how much a warfighter feels they can depend on the system in a vulnerable or in an uncertain situation. And so how much the warfighter trusts the system will directly impact how much they rely on that system and how much they operate that system. And so what we hear a lot is people talking about gaining trust or building trust through testing. And instead, what we like to focus on is trust calibration. Calibration occurs when the warfighter's operational experience aligns with the system performance for a given context. So here you see on the left a color grid which indicates how the system performs for a given task in a certain environment. And so you see some green squares where the system is known to perform exceptionally well, You see some yellow squares where the system performs okay, some red squares where the system performance is poor, and a couple of gray squares where we didn't even measure system performance. So ideally, a warfighter's trust is properly calibrated when their reliance on the system matches system performance. That is, they use it when it's an asset, they apply more scrutiny, or potentially even ignore the tool when the system performs poorly or when system performance is unknown altogether. The reason we talk about calibrating trust rather than building trust is illustrated by the following couple of examples. Consider this warfighter. This warfighter's trust is reasonably properly calibrated. We see that they trust the system in the green squares where it's supposed to, and they look at it with more scrutiny in all other areas. Consider instead a warfighter who overtrusts the system. So that means that they overly rely on the system. In this specific situation, the warfighter uses the system for all scenarios, including those where the system performs very poorly. So this blind reliance can lead to all kinds of catastrophic mistakes. For instance, if a system incorrectly identifies civilian transport as an enemy vehicle, a warfighter could blindly shoot down that vehicle. Conversely, a warfighter could undertrust a system. That is to say, this warfighter fails to utilize the system even when it's an effective tool that would actually improve the performance and potentially responsible employment of the system. This can lead, in easy cases, to operator maybe just having a larger workload because they're ignoring the system. But in more catastrophic cases, potentially missing advanced warnings of an inbound missile or something along those lines. So as testers, what we care about, again, is measuring the operator's trust to predicting how the system will be employed in the field. And we care about calibrating that trust correctly because over trust or under trust undermines successful AI adoption. This means that for us as testers, we have to actually rethink test design as part of measuring system reliance. We must actually give the warfighter a choice whether or not to employ the system, whether or not to rely on the system, which is has not been part of traditional tests for the department.
Hey, Jane, sorry, we're a little bit over time right now. So if you don't mind finishing up this slide and wrapping it up, that would be great. Thank you.
Okay, no problem. Actually, this is almost the last piece of this is just calibrating workload. And similar to trust, workload is something that we want to calibrate as far as the amount of resources that the warfighter spends. That could be mental resources or available time, et cetera. And so what we usually want to have is a balanced workload that is critical to the warfighter effectively employing the system. And so here, just like we don't want to build trust, we also don't necessarily want to minimize workload. We want to calibrate it properly. So here, if you have a warfighter, for instance, with a workload level that is too high, then that's a fairly well-known consequence. They become overwhelmed, they shed tasks, they sacrifice performance on some tasks for other tasks. We also know that workload that is too small is also problematic. So we have warfighters that may become inattentive, that are not mentally engaged. So what we're really looking for is a proper calibration, again, of workload that has the warfighter engaged and effective. And so the very last concept I'll touch on before I finish is function allocation. So function allocation is the idea that the tasks are assigned, and I'll just race through this. They're assigned based on who is actually capable of accomplishing a task, who is actually assigned the task, and who is held accountable for the task. And the pieces that we look for here, again, the agents are actually capable of completing the assignments that they're given. For instance, AI is often introduced when human speed of decision-making is too slow. We also really want to avoid leftover allocation. We want intentional task allocation. So what we see a lot at the JAIC is that we pick tasks to automate that are easy to automate or that are really boring for the human or very repetitive. And as a result, the human is left with kind of this this puzzle that's lacking context often, of tasks that were left over for them to do. And then finally, we want to avoid things like invisible work. We want to make sure that we carefully account for all of the work that both the human and the automation potentially are doing. I'll stop here, Dan.
Great. Thank you, Jane. And I think this is actually a good transition into our panel. So we're going to go until 4:05, everyone. I think that is what Rebecca told me. So for this next part, we don't have any presentation or speakers, but I've assembled our brain trust of our speakers today, as well as Dr. Purnima Madhavan, Dr. Chad Bieber, and Ms. Rachel Haga, all of whom have great expertise in either directly using systems like Chad or as one of the thought leaders in socio-technical systems with Purnima. And we also have Ms. Rachel Haga, who has her master's degree in aerospace engineering with a particular focus on human systems integration, with a lot of work on both AI and complex automation in aviation. And the goal of today's panel discussion is to try to talk to the audience of testers across different organizations about what they personally can be doing right now in order to prepare for the challenges of testing AI-enabled capabilities, and maybe what their organization should be doing over the long term for some of these harder problems. And so I had a couple questions out to the panel ahead of time. And I think the first one is this idea of low-hanging fruit. What's something that the working level testers in the audience can start implementing on their projects or programs today? And Dr. Madhavan, I believe you had a good response for this, so I will hand the microphone over to you. And again, just for the rest of the panel, if you'd like to jump off of what someone else has said, just please raise your hand. Okay, so Purnima, go ahead.
Dan, it's great to be here. Thank you for having me here today. There's a huge body of work that exists, and that became obvious just listening to the three panelists today. But anyone that's been following the work in this area knows there's about 3 decades of work that talks about trust issues, reliance, assurance. So I think the lowest hanging fruit for the community, not just for T&E, but the community in general that's interested in this, is to bring people to the table. And what we're lacking is any kind of consensus on what these models are. And what I mean by that is, so there's a lot of difference between someone that's working with, say, a level 2 autonomous system, which is like self-driving car, or just adaptive cruise control and lane keep assist, versus someone that has to work with a humanoid robot. And what they're often faced with is, well, okay, there's all this body of trust, work on trust. There are these trust skills that can be used. There are these metrics where we can measure assurance and reliance, etc. But what do we use where? So I think the best thing, the lowest hanging fruit for us as a community, which is the T&E community and the research, the scientific community, is to start creating ways for people to come together and build consensus on what can be applied where. So what we need are comprehensive models and frameworks that synthesize the correct state of science on human interaction with AI-enabled systems and map concepts like trust, assurance, reliance issues to specific categories of use cases. So which of these applies to, for example, a level 2 autonomous vehicle versus which of this applies to a humanoid robot? And then develop a toolbox of measurement techniques for variables like trust assurance that can also correspond to specific categories of use cases. So what we need to do is triangulate different approaches, different tools, and then be able to apply them to specific contexts instead of just having this generalized body of work right now. And the reason I think this is low-hanging fruit is because this work already exists. And there are several people right here in the panel on the audience who are working on this right now. So what we need to do is be more proactive about bringing people together, creating channels, forums for people to start talking and to develop these consensus models that can be readily applied. Over.
I completely 100% agree. I think it's a great tee up actually for inviting the audience to a consortium we're putting together. We were going to have our inaugural event as one of the lunch sessions here at DataWorks, but we decided we needed to push it back a little bit. But yes, I agree. We should be getting different trust researchers out there together. And I promise this was not a plant, everyone. But yes, so I completely agree that we need to, there's a lot of different definitions out there. There's a lot of different tools out there. Some of them are more appropriate for certain contexts. And just getting all that together, all the stuff that already exists into something accessible, for the workforce, I think would be not a huge lift, but a huge boon to the department. So yeah, thank you for that. Rachel, I see you have your hand up.
Yeah, no, thank you so much for having me. And I actually just wanted to build off this idea of really taking advantage of resources and knowledge that already exist. During Dr. Cummings' pretty fabulous keynote, she really highlighted one of the issues was mode confusion. So how with the Tesla autopilot, it was reverting control to the drivers and they didn't really understand why. And she called out that this is not a new problem. Commercial aviation's been dealing with mode confusion for decades. And pilots dealing with autonomy in the cockpit, it's not just limited to mode confusion. There's a ton of issues they've had to face. And so echoing Dr. Trent as well, I think that there are a ton of failures of past complex systems that have a lot of really valid lessons that we can learn from them, how people are going to interact with these systems, where the failures are going to pop up. In a lot of cases, I think, the humans not being taken out of the loop, they're just kind of being assigned monitoring tasks. So, aviation's had to deal with this. How do you keep a pilot engaged in a 3-hour crew cycle where they don't really need to do that much? You have to use procedures and checklists to keep them in there. If you're trying to keep them in the loop so that they can intervene in case of emergency, you're probably going to need training to build and maintain expertise if they don't manually fly very often. And this is going to be true with people working with AI, where the AI is doing most of the task most of the time, and then a sensor fails, and suddenly the human has to intervene. There are standards on how to kind of have standard displays, guidance on how to do crew resource management, and how to have the underlying architecture be understandable by the pilots. And I think that out of this community, there's a ton of lessons that we can learn and draw from and pull into this community and not really have to learn from scratch here.
Great. And so I see our resident pilot, Chad Bieber, had his hand up. Chad, do you want to respond?
And for great. I liked that Jane ended on the assigning function allocation. And I also liked the next thing I went to talk to was remembering that there are other places that people who have these problems that we can use as other resources. The thing that I wish was done most often in the systems that I'm looking at right now is that we intentionally chose what tasks we wanted the AI to do and what tasks we want to do. And what I want to note is that we've been thinking about this for a really long time. The fits list, what are humans better at and what are machines are cut from a 1951 paper. 70 years ago, we were learning how to do this. And I don't have changed the fits list much. It might have made some minor updates to it, but I don't radically altered it. And to run off and charge and build new AI things without thinking about what we've done over the past 7 years is, thank you.
Thanks, Chad. So I don't see any other hands from the panel. I'll just leave the mic open for a sec if anyone wants to chime in. But otherwise, I think the other question is, there's these low-hanging fruit, getting people together, building a toolbox, following the existing guidance out there, or at least in similar fields like in complex aviation. I agree that's all good. But some of the problems I think we're facing are much bigger in scope, that they're going to require some real serious thinking and some maturing of technology, maybe in instrumentation, like Stoney had mentioned, or in other things. But Chad, I think you also had some thoughts on what are some long lead things organizations should start investing in.
Absolutely. The big challenge that I see is defining workflows for tasks that you can't actually do with people right now. So what do I do this? I'm doing computer vision tech at work right now. When you apply that to videos, to full motion video things, humans are really experienced at watching TV. That might not be a good statement. We're really experienced at watching TV and understanding what is happening as moving picture in progress. We are not very experienced at, for example, looking at all of the satellite images the ocean over the last 10 years.
Chad, your mic just cut out.
Am I?
You're back.
Again now.
You're back.
And every satellite of the last 10 years, but computers could do this for us. Turn this information about speed up.
Chad, I think Russia doesn't want us to know your wisdom. You keep cutting in and out.
Pacific Ocean and not Ukraine.
Sorry everyone for the technical difficulties. Yeah, Chad, I don't think we got much of that. Does anyone have, for what we caught of your response, Chad, I'll try to sum it up, that there are things, and please correct me if I'm wrong, but there are things that we're good at as humans that we have in our workflows. But now there are these big data problems, like we have hundreds, thousands, millions of hours of full motion video. We're not good at watching all of that, and now we're starting to develop algorithms that can do that. But is your question about how do we design the human workflow around these new capabilities? Not sure if I'm capturing that right.
How do we do the AI human workflow on tasks that are complex?
Okay. The critical part of that you cut out, and the rest of it I got. Jane, or sorry, Rachel, that's your hand.
Yeah, no, and I think I wanted to pile on to the idea of function allocation and being deliberate in how we design systems, and I think really designing for making sure that our assignments are to achieve some optimal mission performance as opposed to just maximizing technology capability. I think a lot of times as engineers, and I am absolutely guilty of this, like you see a problem and you're like, I can automate 3/4 of that. And you never step back and reflect, is automating 3/4 of that the best way to actually get the best performance out of this system when it has to work with a human? And so I think really kind of taking a step back and saying, what is the best use of AI as one tool in our very large tool set, as opposed to, I have this AI hammer, please make everything a nail.
So I agree with that. Do you think, what do you think organizations should be doing about that?
I mean, in terms of what should they be working on today for long lead problems, I really think one of the biggest problems we're going to face is people often associate HSI with like ergonomics or interface design. And while both are super important, that's not really all of it. I think the underlying logic for a lot of these softwares is going to impact how people can perform. And it's not something that's going to be able to fix with like human factors fairy dust on something you identify in operational testing. And so the algorithm selection that you make may have a huge impact on how the human can interact with it. And so I think research dollars should really be going towards basic research to really understand how things like mission performance is impacted by humans interacting with different types of underlying AI architectures. If they have to make a decision with an AI-enabled system that underlying has a neural net to do a particular task, how does that impact, how does that differ from maybe just working with the basic regression in terms of their ability to understand and predict and work with that particular system? Because we don't have 5 or 10 years to start testing those systems. These are decisions that have to be made at the beginning. And so I think basic research there is really needed very, very soon.
Great, thanks, Rachel. Jane, I see you have your hand.
Yes, so I wanted to pull a thread that you and Chad mentioned, and then Rachel actually also just kind of continued unknowingly pulling that same thread. One of the things that either you or Chad said were that we're not good at watching 9 screens, therefore we shall automate something. And something that Rachel just mentioned as well, I'm a proponent of the idea that we actually don't know if we're good or not at doing these tasks. For the most part, we actually have no idea. We don't usually routinely measure how good our humans are at the jobs that they're doing. And so as Rachel talks about, human and AI, for instance, together accomplishing a common goal, I still think we don't even know how to really define our goals necessarily, and that's where we should be paying attention. So we have the Jaker finding that's specifying requirements, whether it's for AI or for an AI human team of some kind or AI human unit, if they're not teammates, that's actually very difficult as well. We don't know how good some of these models have to be to help the human accomplish their mission. Over.
Great. Yeah, thank you. Purnima?
So I'm just going to pull the same thread a little bit more, this whole idea of what do humans do well and what don't they do well and what can we do to support it? So the question here is, under what circumstances do humans need more or less information from AI-enabled systems? So we know there's already a lot of work being done on transparency and explainability, which is good and important. But I think the part that worries me is the flip side of that, which is in this rush to make things more explainable, more transparent, are we crossing into that the domain, the section where it's just too much for the human to deal with? And there is a lot of work in behavioral science that talks about how humans are just not very good at dealing with a lot of too much information. So where is this dividing line between just enough information, just enough explainability, and just too much? And there are, I can think of 8, 10 more pieces that we need to consider when trying to figure out what to tell people and how much information, which includes things like task complexity, interdependencies within tasks, criticality of decisions, timelines of decisions, adaptability. And I know one of the speakers talked about potential to change courses of action during a task, and then innovation creatively. So there are just a lot of variables that need to be factored into this equation. So it's not just, I think more effort, more energy needs to be put into the whole transparency, explainability part of AI-enabled systems.
Great. Completely agree with everything everyone is saying. I think this is an important thread to tug. I guess for the last few minutes, I wanted to zoom out a little bit and talk about the department, as a whole. Are there any trends that you're seeing in the department, other than not really making an investment in HSI, that concern you? So, for example, for me, I hear people talk about the need for building trust all the time when, as Jane mentioned, we really want to talk about calibrating it. Is there anything like that for any of you? Purnima, it looks, at least my screen is showing you. Okay, yeah. Chad, I saw a hand very quickly.
Yeah, I'll take a hack at that. I appreciated, maybe my mic will stay working this time. I appreciated the jab at learning and the other colloquialisms we throw around at AI. One of the problems I've seen encountering people who are trying to figure out what to do with machine learning algorithms is a continued persistent belief in the myth that they keep learning. And I think this is something that falls into vocabulary. Can we correctly describe what we're doing with the new tools we're bringing out and how people should expect them to behave, or are the words we're using getting in the way of that? Artificial intelligence, machine learning, intelligence in general, things like that that suggest meaning to people that might not actually be there under the surface. Over.
Struggling to find my mute button. All right, and Rachel, you had a hand, but it went away.
Yeah, for time, I think I'll.
Great. So we're right against our new deadline. So just as a closing remark, thank you all for our speakers and our panelists. I think this has been a great conversation. I think getting experts in the same room from different organizations is really important. I hope we can continue this conversation in other venues and keep sharing the work we're doing. I think this is a critical challenge the department needs to get right. So thank you all again. Thank you in the audience for listening to us.